All right, so new definition. Let G be a group if there exists an element A in the group such that for every element in the group, that element is equal to A to the power of n for some integer n, then the element A is called a generator of the group, or we say that A generates the group. A group is cyclic or cyclic if and only if it has at least one generator. Now, if the group G is generated by the element A in the group, we write that G is equal to the group generated by A, and we denote this by enclosing the element A in angular brackets. So new definition. Let G be a group. The order of the group, which is denoted enclosing the symbol for the group in absolute value signs, is the number of elements in the underlying set G. That is, the order of a group is the cardinality of the underlying set. Now, every set has a cardinality, but that cardinality is only the order if that set is a group under a given binary operation. So as an example, the integers under addition is a cyclic group of infinite order so proof, let n be a positive integer, then 1 to the power of n is equal to 1 plus 1 plus and so on, so that there are n factors, and this is simply n times 1. If n is 0, then 1 to the 0 power is 0 times 1, which is 0. And if n is a negative integer, then 1 to the power of n is the inverse of 1, which is negative 1, to the absolute power of the absolute value of n, which is the absolute value of n times the number negative 1. So for every integer, that integer is equal to 1 to the power of n, and hence the integers is generated by the number 1, where the cardinality of the integers is the transfinite number Aleph null. It is countably infinite. So the integers is a cyclic group of infinite order. So new theorem. Let G be a group and let A be an element in the group. Then the group generated by A, or for now I'll call it the set generated by A, which is A to the power of n, where n is an integer, is a cyclic subgroup of the group G. So proof. Clearly, A, which is equal to A to the power of 1, is an element in this set. And so the set is not empty. Now let G sub 1 and G sub 2 be two elements in this set. Then there exist integers r and s such that G sub 1 is equal to A to the power of r, and G sub 2 is equal to A to the power of s. So G sub 1 times G sub 2 inverse is A to the power of r times the inverse of A to the power of s, which is A to the power of r times A to the power of negative s, and this is A to the power of r minus s, where r minus s is an integer. And hence, for every two elements, G sub 1 and G sub 2 in this non-empty set, the product of G sub 1 with the inverse of G sub 2 is in this set, and thus this set is a group, is a subgroup of G. And further, this group is cyclic by definition, and therefore the group generated by A is a cyclic subgroup of the group G. So let's look at an example. For every integer n, the group generated by n is simply the group of integer multiples of that integer n. And so the integer multiples of the set of integers by the integer n is a cyclic subgroup. Of the integers under addition, and this is true for every integer n, where in this case the set of integers itself under addition is a cyclic group. So notice in particular that the group generated by -1 is simply the set of integers which is also generated by the integer 1. And so the cyclic group of integers under addition is generated by exactly, or rather there are exactly two generators for the integers under addition, 1 and -1. Okay, so new theorem. We'll prove that every cyclic group is abelian. Proof. Let G be the group generated by the element A, and let G sub 1 and G sub 2 be any two elements in the group. Then there exist integers R and S such that G sub 1 is equal to A to the power of R, and G sub 2 is equal to A to the power of S. So the product, G sub 1 times G sub 2, is A to the power of R times A to the power of S, which is A to the power of R plus S, and this is the same as A to the power of S plus R, which is A to the power of S times A to the power of R, which is G sub 2 times G sub 1. And therefore, the cyclic group G is abelian. Now, the converse of the previous theorem is not necessarily true. For example, the set of rational numbers under addition is abelian, but is not cyclic. Let m over n be any rational number. Then the cyclic group generated by m over n is the group of integer multiples, or rather integer powers, of m over n. Notice that the number 1 is not in this group unless m is equal to the absolute value of n. But then the group generated by m over n is simply the additive group of integers, which is not the set of rationals. And so the rational numbers does not have a single generator, and so it is not cyclic. Now, if the group generated by A is a subgroup of G, then this cyclic subgroup of G is the smallest, and by this we mean the most exclusive subgroup of G that contains the element A. So let H be a subgroup of G that contains the element A. Then A squared, which is A times A, must be an element in the group, as we must have closure. And then A cubed, which is A times A squared, must also be in the group. And in general, A to the power of n must be in this group for every positive integer n. Also, the inverse of A must be in the group, so that A to the power of negative n must be in the group for every positive integer n. And the identity, which is A to the power of 0, must be in this group. And hence, the cyclic group generated by A is a subgroup of H. So the cyclic subgroup of G generated by A is the smallest, that is most exclusive subgroup of G that contains A, and this means that any subgroup of G that contains A must contain the additive subgroup generated by A. Okay, so we'll end here for today. Next time we will continue to look at cyclic groups and look at the detail of their structure. So I hope you have enjoyed the 17th lecture. Thanks for watching.